Hello, ladies and gentlemen. I am sorry that this is late. I've been having some technical difficulties trying to get rid of the blue paper. All right, we're going to do 5.1. This is just a review of the natural log function and the derivative. Our objectives are that we're going to remember properties of our natural log functions from way back in pre-calc, and then we're going to find derivatives of our natural log functions. All righty. Oh, that's weird. I wonder if I can kill that. Ooh, look at me go. Alrighty, so if you remember from pre-calc, if I have the function y is equal to the natural log of x, this is true if and only if e to the y is equal to x. And remember that the base is e, and so this would be how we write our expression. Alright, if you talk about the graph of the natural log function, remember that I have a vertical asymptote at x is equal to 0. It crosses the x-axis at 1. So if I have, say, the natural log of 0.5, it's going to be a negative value because this portion is under here. All of this is undefined because you can't take the log of a negative number. Alrighty, so a couple other things that we need to talk about. The domain of the natural logarithmic function is 0 to positive infinity. Doggone, my stupid computer. It hates me. All right, let's see if we can make it quit doing that. The range is from a negative infinity to a positive infinity. Other things that we know about f of x is that it is continuous. We know that it is increasing over the domain. We know that it is one-to-one. And if you'll remember from pre-calc, one-to-one means that both the original function and its inverse are both functions. We also know that it is concave over its domain. Alrighty. So now let's go back and talk about our properties of logarithms, because sometimes if we are going to take derivatives, it's easier to do the properties of logarithms first before you try to take the derivative. Alright, I'm just going to leave that there and maybe it will go away. So the properties of logarithms, remember that the natural log of 1 is equal to 0. The natural log of a negative number is undefined. Oops, forgot the equals. Undefined. The natural log of a times b is the natural log of a plus the natural log of b. The next one would be the natural log of a value raised to an exponent. The nice thing is the exponent comes out front, and then I have the natural log of a. And I think, oops, I forgot one. The natural log of a divided by b is the natural log of a minus the natural log of b. Alrighty. I'm going to put this, even though it's not really a property, I'm just going to write this here for lack so I don't forget it. But the function is the natural log of x. The derivative is going to be 1 over x. And for whatever bizarre reason, I have the second derivative using my quotient rule or the chain rule. Sorry, if I rewrote this as x to the negative 1, it's going to be a negative 1 over x squared. So I'm not exactly sure why I wrote the second derivative, but there you go. Alrighty, so let's go back and review while we're at it get my paper to be straight, our expansions of logarithms. So it's been quite the afternoon. Math meetings, flat tires, you know, all those fun things on a normal daily basis. All right, I'm sorry, I have to kill this thing. You guys can't see it, but it's in my way. Alrighty. So if I were to have an expression that said the natural log of the square root of 3x plus 2, then this is, because the exponent is a half, then it would be the natural log of 3x plus 2 to the 1/2, and this is 1/2 natural log of 3x plus 2. And then that would make taking a derivative easier if I needed to later. the natural log of 6x over 5, if I wanted to expand this, would be the natural log of 6 plus the natural log of x minus the natural log of 5. Remember, using the properties of logarithms, everything that is divided becomes negative. And then if I want to make one a little bit more entertaining, x squared plus 3 quantity squared over x to the cube root, if we really want to make life exciting, okay, and I'm not going to do it in steps, I'm going to do it all in one fell swoop. So it's going to be 2 times the natural log of x squared plus 3 minus the natural log of x minus 1/3 the natural log of x squared plus 1. How's that for expanding something all in one fell swoop? Alrighty, so if we want to talk about calculus, and I've already gone over it, last year we did a lot of work with u and u prime, but basically if I want to take the derivative of my natural log of u, okay, it's going to be 1 over u times the derivative of du dx. And you could write this as u prime over u, but basically all you really have to remember is the chain rule. So I'm actually not going to do our examples using the u's. I'm just going to manage it using our chain rule. And then just for posterity, to show that logs are and exponents are the inverse, if I were to have an integral that said 1 over x dx, then this would be the natural log of x plus c. Alrighty, so let's do a couple of derivatives. We're going to do, in this particular chapter, I'm going to save all of the integrals for later, so we're going to do most of our derivatives first. So if I want to take the derivative of the natural log of x squared plus 1, and again, I'm not going to do the u because I don't think we need to at this point, then it's just going to be 1 over x squared plus 1 times the derivative of the inside, which is 2x. And so then my conclusion statement would be the derivative of f of x is equal to 2x over x squared plus 1. So that's pretty easy. Alrighty, cruising right along. If I do our next example, and I want to take the derivative of the natural log of x to the third, again, remember this is the chain rule, so it's going to be 3 times the natural log of x raised to the second times the derivative of the inside, which is 1 over x. So you could rewrite this as 3 over x times the natural log of x and then quantity squared. Alrighty? And yes, I'm not going to write my conclusion statement. I know it's scandalous, but I'm not going to just in the interest of time. So now is when we're going to do an example of our properties of logarithms, because we can use those, sorry, that guy doesn't go there, to make an expression that looks nasty to clean it up a little bit. So let's say I want to take the derivative of, and then I'm going to have x times x squared plus 1 quantity squared over 2x cubed minus 1. So when you look at that, it looks super hard, but if I use my properties, then it's actually fairly straightforward. So I'm going to split this up first. So I'm still wanting to take the derivative, and then this is going to be the natural log of x plus, because I have a multiplication, 2 times the natural log of x squared plus 1 minus 1/2 the natural log of 2x cubed minus 1, and that's the stuff that I want to take the derivative of. So now if I just work my way across, the derivative of the natural log of x is, I'm just going to write this like this. I'm going to have 1 over x. The derivative of this is going to be 2 over x squared plus 1 times the derivative of the inside, 2x, and then minus 1/2 times 2x cubed minus 1 times the derivative of the inside, which is 6x squared. And then I would clean it up a wee bit. I would turn this into 4x, and then 2 goes into 6 3 times. So I would say that my derivative of f of x is going to equal 1 over x plus 4x over x squared plus 1. And then I have minus 3x squared over 2x cubed minus 1. Now, I would probably stop here. But remember, the only reason that you would need to continue would be if this was a multiple choice portion of the test and this particular solution did not match the multiple choice. If that were the case, then you would have to continue to simplify this, which is possible. It just becomes a little bit entertaining. Alrighty, I have one last example. See if I can get my page straight. So my last example, and that really is spelled right, it just looks bad. Whew. So we want to find the derivative. And we're going to do y is equal to x minus 2 quantity squared over the square root of x squared plus 1. I could do the quotient rule, but I really don't like having to use the quotient rule. So instead, what I'm going to do is I'm going to take the natural log of both sides so that I can actually use my properties of logarithms. So I'm going to write that the natural log of y is equal to, and I'm going to go ahead and split this up as I do my properties. It's going to be 2 times the natural log of x minus 2 minus 1/2 times the natural log of x squared plus 1. Well, now if I take the derivative, I have an implicit differentiation chilling out right here. So I'm going to write that I'm taking my derivative, so my grader knows what I'm doing, and I'm going to get 1 over y dy dx is equal to 2 over x minus 2 times the derivative of the inside minus 1/2 times x squared plus 1 times the derivative of the inside 2x. Okay. Remember, the goal is to solve for dy dx, so I'm going to clean this up a little bit. Those 2's cancel. So I'm going to get my dy dx is equal to 2 over x minus 2. Yes, I know I don't have him written down, but I show him what I'm going to do with him in a minute. Then I have x over x squared plus 1. I'm going to put these guys in parentheses. Now I'm going to multiply both sides by y. But I can't leave it like that because now I need to substitute y into here. So I'm going to say that my derivative, dy dx, is going to equal 2 over x minus 2 minus x over x squared plus 1. And I'm going to multiply by the original y, which was x minus 2 quantity squared over the square root of x squared plus 1. And again, the same situation, sorry, I was using hand motions and you can't see it. The same situation would happen if you were taking a multiple choice test and this was not one of your choices, then you would have to continue to simplify. But at this point, I could find the slope of the tangent from here because this would be a fairly straightforward substitution. Alrighty, thanks for being patient with me today. That is it. I will see you tomorrow.